The following content has been provided by RWTH Aachen University.
All right. Good morning, everybody, and welcome to the last class in the DIS1 cycle. Today, we're going to wrap up this class by talking about interaction design notations. But as always, just a very quick review on what we covered last time to get your mind back into where we are. We did complete the 10 golden rules of interface design and then expanded on a couple topics. One was Jeff Johnson's model of the 3 human deadlines, the 0.1 second, the 1 second, and the 10-second intervals. We then talked about some performance hits that you can avoid as an implementer, even when you're working at lower levels of your code, because they will still have an impact on the user interface. And then we discussed latency in particular, and I tried to show that latency is quite different from performance. That it could even be we looked at a system from the 1980s that, if you simulate it today, because of the new kinds of interface standards, especially serial protocols like USB and HDMI, and the increased processing happening in the peripherals, you can actually introduce latency, even though you're putting through a lot of data, but the time that it takes a single bit to travel through the entire chain of all these high-powered conversion states can take quite a bit. All right. So today, interaction design notations. The point of this is that we've now learned quite a bit about how to design a user interface and how to, we know certain aspects of how the user interface should work. And this goes beyond just saying, put this button here, right? You often will encounter in your career, if you're working in HCI, you'll encounter people who have no idea of what interface design means, and they'll say, oh, you're just pushing buttons around. And that's sort of almost the least interesting part of interface design. So interaction design is much broader, and we need to specify a lot of the things that we want to behave in a certain way in the UI. And for that, we need a language. We need a way to express that, right? A formal system, a notation. And that's what we're going to talk about today. There's a whole bunch of notations, and quite a few of them will seem familiar to you from your computer science curriculum, and others might be new to you. First of all, what we're talking about today is in part based on the chapter on notations in Alan Dix's excellent textbook, Human-Computer Interaction. We've mentioned this book before. You've had a chapter to read out of this. And I can just reiterate, this is a great book, the best, I think, single volume textbook to catch up and getting started in HCI as a discipline. So that being said, let's take a look at some notations. Here's an example that is trying to show why we bother about thinking about user interface design, specification, languages. When we have programming languages, I mean, by the time we write code, we are specifying exactly how an interface should work. Let's see if you can maybe think about some of the problems that you might see with this notation, not whether this is a good program or a bad program and what it does. I'm not talking about the UI that this program generates, right? Whether please enter a number is the right prompt here. I'm talking about by writing your code like this, what are some of the problems you could run into by specifying your UI in this way, in the programming and in the code itself? I'm not seeing you, but I'm seeing that you're there, Pascal. Do you want to take a stab at this, Pascal Rabe?
Yeah, I guess so. I mean, if you put it in the programming code, you might not be able to be as adjustable as you would be if you do it in the app development. And I guess if you just have a rigid cage you build and just a basic principle. You can adjust it at any time and just build the app around it, and you don't need to readjust the code again. And I guess code is something most people are not common or like known with, and they don't know what to do about it. And sometimes code is just badly commented, and this just leads to more errors, I guess.
Yes, yes. So that's a good description. What we're seeing here is essentially a mix of UI specification and back-end code, right? Business logic, as people like to call it, that, right? Business software, right? That software has very simple business logic. The business logic of it is that it basically computes n times n, right? That's the algorithm. That's the sort of the thing that this thing performs. Everything else is UI. And in this simple 3-line code here, in BASIC, we are essentially putting everything into one file. We're mixing the UI specification and the very limited business logic here. So why is this a problem? Well, as you already said, changing things could be tricky. In order to change the UI, you need to go into the source code, which might easily mean that you change the business logic behind the program, which you may not want. Let's say you just want to fix a typo in a text command here, or in a text line, then you might suddenly change the actual code that executes and that expresses the business logic. So that's not good. Other examples, let's say you want to take this program is so successful that you want to translate it into German. So you need to go into this code, and you need to be a programmer in order to change the language, even though somebody who is good at translating would be a much better person to do that. So why can't they work in a separate file that contains all the strings, the text, and then that gets merged together at runtime, or even at compile time, but it is specified separately. So that's what we're looking for, right? We're trying to make sure that we have a compartmentalization of the UI and the actual behavior of the program. So ideally, a good way to test whether you're doing a good job with that is to say, could I completely swap out the user interface to my program? For example, could I move from a graphical UI to a text-based UI, or could I move this program easily from the Windows UI toolkit over to let's say the Mac UI toolkit, right? If that is possible, then you've managed to pull the business logic out and separate it nicely from the interface. So while code is extremely precise, right? It tells the computer exactly what to do. You can't get much more precise than actually writing code. That's what gets executed in the end. It also means that if you put your interface into code, then the code becomes essentially your design document, right? And code tends to be actually more resistant to change than we might think, right? Because rolling changes into code means a lot of regression testing against, did we break anything, etc. And so that's another one of the problems that we face if we do it this way. So that's why we have UI specification languages. We don't want the normal mixing up of the UI and algorithms, which is what you get in your normal programming languages when you include some kind of standard IO library or your print commands in your favorite programming languages. And we don't want the system, the things that the system does and the things that the user does to be hard to distinguish anymore. Another thing that is also tricky, I'm sure you've written code that needed to take some user input already, right? And if you wanted to do this right, if you wanted to do this really robustly, you would actually have to do a lot of input validation, right? Did the user actually type in a number? Did they use a comma instead of a decimal point? Did they type in letters instead of digits? Blah, 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 blah. Is the number too high, too low, negative? There's so much stuff that you need to check on a simple input that it can quickly get out of hand if that's all in your business logic, right? You want that to be separated out, and by the time you get to your logic in your code, it should know that it's working with clean data that got input by the user, for example. So the first step that we can do without actually moving to a separate language is to just say, I'm going to structure my code appropriately, right? I'm going to have my own classes, or if you're in an embedded system, you might be still programming with a procedural language. So your own, functions or whatever it is that collect all the user interface side of your project. This is easy, right? Then the second step then is, we know that languages are already, that every language is good at some things and bad at other things. And we are now specifying the program logic in code, that's fine. And we're also specifying the UI in separate classes in the same programming language. And clearly a programming language is not necessarily the best language to express what's going on in a UI. Just think about the amount of code you need to write to put let's say, a button into a user interface if you're doing it programmatically. If you've never done that, then you'll see this in DIS2 if you join us next semester. But let me tell you that it's a lot of effort to build your interface programmatically line by line, because you're basically specifying the visual layout and relations between, like, if this gets clicked, then this should, this other thing there should maybe change color or something. You're trying to specify all this in code, which is messy and not very easy to maintain and keep an overview of. So as a second step, then we might say, well, if we're already compartmentalizing this and putting all our UI logic into a separate set of files, let's say, or classes, why not use a different language that is more geared towards specifying the dialogue properly? And we can do this in two ways. We could do this ahead of time or a priori to actually design the dialogue. So without even having to write code, we could start by expressing our interface design in a language, in a format, in a notation that can then flow into the development later. So you could do this a priori and maybe not even expect it to be automatically interpreted or something. Just say, this is how I'm writing it down. This is a formal notation that a human can read, and they can then implement the right thing to go with it. Or you might have a way to actually express your interface and have it actually automatically translate into code somehow. Right? That's the second step, or the second step. This means that you are in the lucky case that you can actually execute your specification and turn it into code. But this is still quite different from writing your specification of the interface in code, right? So how do we specify user interfaces? So the problem is we need to describe a proposed design for a user interface. We have something in our mind, how we want it to look, which we arrived at by drawing paper sketches and maybe testing them with users. So we have an understanding of how the user interface should work. And we need to basically hand this to the development folks in order to build the prototype around it. Or maybe we are the developers ourselves and we just need to specify this for our own sake, or to document it and still remember what we did 3 months from now. Now, the great thing is here, one approach that you can take to specify a UI is language-based. And computer scientists are great at languages, right? We know how to solve problems by coming up with the language that gets parsed and that has certain meaning and syntax and semantics, and it translates automatically into some other kind of construct. That's our bread and butter as computer scientists. So we can use formal languages. We can also use natural language to describe them, or we can choose something in between that's a little bit more formal than a natural language expression, but not quite as mathematical as a purely mathematical formal notation. And a lot of the techniques that we know from computer science that you've learned about, of course, then apply, right? Now, the problem here is this approach will work really well for historical UIs, let's call them, or command line based UIs. If you take a Unix command line program, you have a you have a very simple flow of you know, digits and symbols back and forth in a serial way. The computer, you know, puts something on the screen and then the user types something back. So that's pretty easy to model with the methods that we know to, you know, in formal languages in computer science, because it is based on semiotics, right, on symbol manipulation. But it's much more tricky to actually specify a graphical user interface in the same way using a formal language. And we'll see why that is the case. One of the reasons is, just imagine what you could be doing when you are at a graphical user interface. At any point in time, the user could, you know, open a help menu, or they could drag something over from another application, or they could switch to another window. So a lot of things can happen in parallel and alternatively. So there's much less of a clear sequence that we step through in the interaction. So let's see what kind of formal notations do you guys remember from your classes? Does anybody have any formal notations that, you know, your favorite formal notation from your computer science classes up to now? Or maybe not so favorite, that's fine too. Just put up your hand if you have a formal notation that you remember from your various computer science classes, and we'll see whether that will be one of the things we can use for interface specification.
So I'm not exactly sure what you mean, whether you're talking about programming languages or, for example, what comes to mind first in my mind is hypertext markup. A markup language is just HTML, which is useful for specifying user interfaces. Not really good at it. It's mostly text formatting language, but seeing as basically all of the web, except for the PHP parts, are written in it, it is a powerful user interface language, I would say. Also, there are other things like Java, which I heard from you. It's really funny that has, like, I think it's called Swing, the user interface programs. That works. I mean, the fundamentals are basically always the same, working with panels and specifying a lot of attributes of like text and letters and stuff. Yeah. So you're absolutely right. First of all, Swing, of course, is a perfect example. It's one that we'll actually be covering in DIS2, and that is the UI toolkit, right? The user interface toolkit that, or one of the user interface toolkits that you can use in the Java programming language. So it's a library of a class library of widgets that you can put on screen, and that then will send events, and you can help them process these events, etc. So I was more talking about formal languages and formal notations, maybe. So less from a programming point of view. You mentioned HTML, and HTML is a good example because HTML developed out of SGML, right? The standard graphics markup language, or simple something markup language. It used to just be a markup language that was used to structure a document semantically, to say, this is where the header is, and this is where a list begins, and this is where a paragraph begins. And HTML is sort of a derivative of that, and then added in more and more graphical attributes, because honestly, the graphical designers needed the ability to move something, 5 pixels to the right, which was not the original idea of the language. But so from a point of view of specifying a UI, yes, you could see HTML as a way to specify it, but it's already very implementation heavy, right? It's already very clear what the computer is supposed to be doing. But it's an option, yeah. Let's hear Felix. Do you have any other suggestions?
Yeah, maybe something like UML. For example, use a sequence diagram or a state machine to like show the flow of the program and where the user has to make which decisions. Yeah. So that's one more of a formal notation, right? That moves a step away from an implementation language to just specifying things. Yeah, UML and especially state charts will actually be part of what we're going to be talking about today. But there are lots of others. And I'll show you a couple, and I'm sure you'll remember them fondly from your theoretical computer science days. First of all, Grammars, right? We all remember and love the Bacchus Nor form, like grammars to express things for, and these are great for command line user interfaces, because the turn taking that you typically have between a computer and the user in a command line interface is very easy to model because it's a sequence, and grammars are great at expressing certain examples of sequences. So let's take this BNF grammar here that I've written down that just consists of a single line here. Can anybody tell me what this line, some examples of things that this line describes, or what we're trying to capture here with this line? Yeah, Ben, go ahead.
I'm not sure, but I think it defines this expression, perhaps a variable, to be either empty, to have some form of, I think it's some form of recursion going on, where you could add the word atom before it, or where you could add brackets with the expression duplicating itself, basically.
Exactly. Yeah, that's absolutely right. So what you can create with this is ultimately it's all going to lead down to either an atom or some kind of parenthesis, right? Or the empty token, but we expect the empty token to be empty. So essentially it's expressing things like an atom and that has parentheses around it, or maybe two atoms with parentheses around it, or two atoms and one is in parentheses, the other isn't, those kinds of things, right? So it's expressing a series of atoms that have balanced parentheses around them. So you, for example, couldn't create anything that has an unbalanced set of parentheses with this expression, with this grammar, which is good, right? That's the idea. So what does that have to do with the UI? Well, here's an example that slightly extends the BNF form into what's called a multi-party grammar. And this is described in Schneiderman's book on designing the user interface. And what it does is it basically says, we're going to just extend the idea of a grammar a little bit, and we're going to tag each part of the grammar, each element, with either a U, which means this is something that the user is doing, or C for the computer, right, where the computer is doing something. So again, take a quick look at this grammar and tell me what it does. Describe what it is doing. Go through it in your head. Think about what you get by inserting things, and it's pretty easy. Yep, Ben, we're having an individual tutoring session today. Oh, look at this. There's more hands. So Ben, I'm going to take Abdul Kabir, please, because that's the first time you're showing your hand. So go ahead.
Yeah. So sorry. Maybe this is opening a session at first, then asking a login to give the username. Then after the username is provided, it's welcoming that user by saying hello.
Yes, it says hello, and what happens? What else?
And hello, like after hello, it says the name of the user provided, the user.
Exactly. Yeah, that's right. Yeah. Thank you, Obadu. That's exactly what's going on, right? So this is basically a two-line interaction where the user enters the string login and his own name, and then the computer responds with hello, Bob, or whatever the user entered as their name. So what you can see here is, if we're doing a command line based user interface, like in a Unix command line shell or a DOS shell, then this works great, right? This is a great way to express these kinds of interactions, because that's exactly how you would essentially break them down into their components. And don't only think about command line interfaces when you have this class of systems. An ATM, for example, like a cash machine, right, that you draw cash from, also has a highly sequential interaction, right? There is also, even though you're not typing textual commands, you're hitting one of 5 hardware buttons on this thing, and then something starts. It shows you maybe a menu on its screen, but there's never a way to do a million different things in parallel, or let me open up a help screen in between, or let me switch to a different application. That doesn't happen, right? So it's still a fairly stringent serialized interaction. For GUIs, this is less appropriate. These BNF like notations, right? They don't work really well because of the highly parallel nature of user interfaces that are done graphically, because lots of things can all of a sudden be done as options. And that would mean that you would need you know, a million different things. Oh, the user could click here, or they could click here, or they could click here, or they could click here. And each of these would lead to a different result. That gets very messy. But let's look at grammars for, let's look at a couple more examples. Here's a, this is a regular expression. And you all know regex, right? So you know what the star means, the asterisk, right? Means 0 or more occurrences of that token. So this is a regular expression that says there's a select line token, then a click token, then a 0 or more click tokens, and then a double click token. Now I'm asking your imagination to run wild and think about what kind of application could describe this, could this sequence be describing? In what kind of application could this sequence be used? I'll give you a hint. Think about graphics applications in this space. When does this action sequence occur? How about, go ahead, Ben. It's you.
I'm not sure. I think it maybe could just be the operation of when you computer and you want to select a specific word in some line of text. And so you just select the line, then click for however many times you want, but always end with a double click, thus selecting like a specific word.
Okay. So like maybe scrolling down a couple of times and then double clicking when I found the word that I wanted to select or something.
Yeah, for example. I'm not sure on this one, but yeah.
Yeah, that could be a possibility. What I was thinking about with this one was that select line was actually the name of the token, right? So it represents the action, and you said it could be a line of text in a document. I was thinking if you choose the menu item in a graphics application that lets you draw lines, like the line drawing tool, you select that once. So you've now selected the line drawing tool. That's the first token. After you've selected the line drawing tool, you need to, in this, in Photoshop, for example, you need to click at least once to set the starting point of the line. And then you can click more times to set more lines, as many as you want, or maybe 0 at all, right? Yeah. And then when you double click, you complete the line and you finish the line drawing and it gets, you know, painted in, for example. So that's the kind of thing I had in mind here. But as you can see, it's not obvious, right? It's not expressing it. This is a high level of abstraction. It doesn't actually, it doesn't have the semantics. It's as we just saw, it's hard to guess what the author here was trying to say, right? What he was trying to describe. So we're missing something, right? We have now a solution for syntactically capturing certain interactions, but we're not expressing the semantics right? We're still missing that. And the other problem, of course, with this is that, and that will always be the case with any kind of formal notation, you will always be at a certain level of abstraction, right? There's certain kinds of actions that you do capture in your notation, and then there are more detailed little actions that you don't capture. For example, if this was a way to select the line or to draw a line in Photoshop or in Illustrator, then we're not talking about the fact that the user is moving their mouse around in between those clicks, which obviously they are, right? We're not modeling that. That's not part of our, this is not how closely we're looking at the interaction here. So high level of abstraction and no semantics. That's one of the challenges here. We're going to take a look at another one. You may have seen this one. This is if you've ever used the Unix command line, Linux, any kind of flavor of that. Mac OS, just open up your terminal, you get the same thing. It's also Unix under the shell, under the hood. So you can use the copy command, right, to copy files. And this is how, if you were to ask for instructions on how to use the copy command, this is what comes back, right? I hope you've all seen this. You're computer scientists. You should have seen this. So CP for the copy command, and then comes a whole bunch of parentheses, these brackets, like square brackets, which tell you that this is optional, right? So this could mean that you can have the -r or in there, or you can not have it in there, because that whole thing is optional, like it's in parentheses. Next up, then you have after the -r, you could have a -h or a -l or a -p. That's what the vertical line is telling you. Or you could have none of these, because also that is another optional part. So this is how this goes on, right? Blah, blah, blah. And then at the end, what you do need to have in the copy command is a source file name and a target file name, or a source file and more source files. This is kind of like the asterisk after it, or the plus sign after it in regular expressions. And then a target directory, right, instead of a target file. So in one case, you're copying lots of files into a directory. In the other one, you're copying one file to its new name and location. So what this is, again, what you're not seeing here, for this you need to read more about the instructions and about the manual, is that the first part tells you the policies of the copy command to recurse into directories. That's expressed here. How it recurses into directories, whether it does that at all, and if so, then how. And then override policies in the second part, right? What happens when you have a file that already exists, right? What should the copy command do? So these things are short and precise. They are so precise that they are actually usable in an automated way to turn into code of some sort. But for humans, they are still pretty hard to read. And as we can still see, we need more information about semantics, right? We're still missing the semantics. If I hadn't told you that these are the override policies, you would have no idea of seeing that. Now, let's look at something that is actually more suited for graphical user interfaces. And this would be production rules. Again, production rules is something you should know from your computer science studies. Production rules are an unordered list of rules. Each rule has the format of a condition. And if that condition is fulfilled, then the action behind it can happen, right? It can fire, if you like, and it can do that at any moment as soon as the condition is fulfilled. In production rules, if we use them for user interfaces, then we would often have the condition based on a state. For example, if the user closes, if there's no document window open, let's say, then gray out the button that says print document, because it doesn't make sense to have it active right now, right? Or it could react onto events. So it could react to an event like, if the user closes the window, if the close button of the window gets pressed, then delete that window from the screen and also gray out the print button, because we no longer have a window open that we could print. The important thing to remember with production rules is that every rule in a production rule system is potentially active, right? It's always ready to fire, so to say. This is great to model concurrency, which we have a lot of in GUIs, but it's bad for sequence. So it actually makes it harder to model things that are sequential, that are typical, command line interactions. So let's look at an example that is event-based here. Going back to the example we had before, I want to model the line drawing tool in Adobe Illustrator, for example. Let's do this with an event-based set of production rules. I mean, we had a solution that was based on a simple grammar, right? And that worked, but how would we do this with production rules? Well, with production rules, you need to use the concept of a token, which is just, it's a convention that you use to think about how your production rules are structured. And we could do a modeling of our line drawing tool in the following way. We would have one production rule that says, if the user selects the clicks on the line drawing tool, then the first rule takes that event and fires and creates a token that we call first. First is just a token. It doesn't actually, there's stuff that's going to happen, right? The menu is going to get selected and the tool is going to get, turned into the line drawing. But we're not talking about that part. We're just talking about the internal management of state in the production rule system. So we've now created internally a first token that we remember. We say, okay, we are in the state of potentially setting the first point of the line, right? That's what this token represents. We're in a state. And in production rules, you need to make these tokens explicit. Now, whenever a first token exists and a click comes in, the click is the token that is created by the user clicking with the mouse somewhere, then the second rule can fire. So it basically checks that the user clicked something, and it checks that we are in the state of setting the first point. And if we are, then it will obviously, set the point and do something in the UI and show the point on screen. But importantly, internally, it will then go to another state, which we call rest, right? This is the remainder of the line that is to be drawn. So it creates this token, this production rule creates this token to model the state rest. And if the rest state token exists and there is another click coming in, so those any clicks after the first click, after somebody selected the line drawing tool, then we stay in the rest state. So we, if you want, we consume this token with this production rule, but we create a new one, which basically keeps on recursing in that state, right? So we remain, if you are thinking about this as a state machine, we remain in that state as long as more clicks come in. And we leave it only if the user double clicks, right? So while we're in that rest state, we continue adding, points to our polyline that we're drawing. And at some point the user double clicks, and that means then, okay, the user is done drawing, setting all the points. We now, I don't know, fill in the line completely that we only sketched while the user was drawing this. Maybe it was just done with a rubber band, a dotted line. And once it's done, we actually paint the line completely in all its glory. And this is set in pointy brackets here, because that is the only thing here that I've modeled that is actually an action that the system takes on the outside world. Everything else was just looking for events coming in from the outside world and setting internal states, right? I didn't talk about all the other things that the line drawing tool would need to do. So what you should note with this is a production rule set. All these 4 rules are active all the time, but the fact that we have these tokens, these helper tokens that we generate and consume, we can manage which of these production rules can actually fire at any moment, right? It's impossible for any of these rules to fire except for the first one when you start up the system, right? Because the first token and the rest token don't exist yet. They can only exist by having the first production rule fire at least once and generate one of those first tokens. So you see that we are imagining in this that we have events coming in that the system somehow detects by the user's mouse clicks or button presses or something, key presses. And we add these to a list of pending events. It's like a queue, right, where these things are coming in, and these production rules then consume these events from the queue. And first and rest are, as I said, internally generated helper tokens, or you could think about them as internally generated events. So we could say the first token, when it's generated, is also kind of like an event that happens, so that if there's a click coming in and the first exists, then we can fire with the second line. All right, so but these, as you can see, since the sequence that I was describing, select line, first, rest, double click, draw line, was very sequential, we had to introduce all these helper events here, these helper tokens, in order to make this work with production rules. This is a nice way to show that production rules are not that great at modeling state. It's pretty, it's pretty unwieldy. It takes a lot of writing to express state properly. We need all these helper tokens and these helper events, if you want, to be around. So production rules are not good at preserving a particular state, but they are good at modeling many things that could potentially happen in parallel. All right. Now, next up, we're going to take a look at your favorite formal notation. I'm sure you've all studied this in your first years of computer science, and that's finite state machines, or automata, or state transition networks. These all describe the same thing, right? So automata theory, automaton theory, I'm sure that's something everybody has fond memories of. And that's what we're going to reuse here, actually, for a practical purpose in user interface design. So state transition networks are a really old tool in the computer scientists toolbox, right? They've been around since the 1960s, and they have been one of the most common tools to simply specify dialogues. And they do a pretty good job at that. That's actually quite interesting. So let's take a look at how they work. Well, as you all know, a state transition network or a finite state machine or an automaton consists of states and transitions, right? You know, bubbles and arcs between those bubbles, arrows between the bubbles. One thing that probably most people get wrong most of the time when they think about state machines for user interface design is the question of what happens inside a state. Because inside a state, as the name says, a state is static. Essentially nothing happens, nothing of major interest in our modeling of the UI. The action, the input of the user and the system response associated with that input happens in the transitions. So put simply, if you write a program and most of the time it sits there and waits for the user to press the button, then that is in a state. That program is in that state in the UI term. And when the user presses that button, an event comes in, and that will likely transition the system to another state where it does something in response to that action and then enters that other state where again it waits on the next action. Think about what we just described with the select line tool menu command. Select the line tool and then click the flip button. In between, your program isn't doing much, if anything, right? It's just waiting for the next mouse click to come in, and these are the states that you are in. So be aware that inside a state, essentially nothing of interest is happening from our modeling point of view, right? From our, altitude that we are modeling at, right? It depends on how detailed we model the interaction, whether we are going down to bits on the serial or USB line, or whether we're looking at the, the big picture here. This will depend on your needs. But from that level of detail that you're looking at it, nothing interesting happens inside a state. It doesn't mean your system is frozen, right? It may be, for example, be playing back a sound file and you're just modeling the start play and stop play actions. So playing back a sound file is something that happens inside a state. So stuff is going on, but we don't model that in action in any more detail than just saying, well, it's going on. All right, so this is great. Because state transitions are great at modeling sequence again, right? So they are, not surprisingly, very similar in what you use them for to grammars, right? Because as you learned in an automata theory, automata and grammars are basically just two ways to express the same thing, right? But it turns out that state transition networks, with their visual representation, are a much nicer way to express user interface states and the transitions between them than using grammars, simply because they are more visual and that you can see exactly what goes where and from where you can go to what other state in your interaction. Let me show you an example, and we're going to stick with the example of a graphics tool, right? Like Illustrator or Photoshop. So here's a very simple state transition network that models a few things. What it models is a simple graphics program that has two commands. One is drawing a line or a polyline, I should say, and the other is drawing circles. So your program starts in the start state. In this case, this is marked by the triangle. We often use another notation for that. It just depends on what you agree on in your project. And then you can see from the start here, we get immediately to the menu state, right? There's nothing that needs to happen to do that. So in this simple version of the STN, we could save ourselves the separate start state actually, and just start in the menu state. But If this got any more complicated, then there might be other things that could happen than just going to the menu state immediately. So that's why it's added. Now, when we're in the menu state, that means the program is in the state that's called menu, right? And then a user action happens. The action is the user selects, for example, the line command, like it goes down the bottom path here, right? So the moment the user selects the line menu item, the line tool in our graphics program, we enter the state line 1. Nothing happens in that. We wait for the next user input. Then the user clicks on the first point that they want to set a line to. That's written above the arrow here. Below the arrow, we have the system response. We create a rubber hand. This should probably be a rubber band, probably. I think it's, we need to check this, Ollie. Maybe that's a spelling mistake. So it creates a rubber band sort of visualization of, this is the first point where you are, and we move into state line 2. If the user does more individual clicks, then we keep adding line segments, right? We draw the next line segment in this rubber band style, right? And only if the user in line 2 double clicks, we draw the last line segment and finish this somehow, which would mean, maybe completing the drawing, and from there on, we would probably go back to the menu state. Alternatively, as you can see on the top there, we could also, the user can also select a circle command from the menu and then click on a center point, which would create a rubber circle. And then he would click on the circumference of that circle that would basically then, and that would draw the circle and finish that drawing command. All right, so that's a very simple example. I wanted to show you a more significant example that is actually from a real project. Many years ago, I built a system that lets you conduct the Vienna Philharmonic. I think we talked about it briefly early on in this class, and it's an interactive music exhibit, right? And in order to design that, at some point we had to specify for ourselves and also for our client, the museum, what the actual interaction is supposed to look like. So we're going to first maybe take a quick look at the video so that you can see the sequence of interactions that the user experiences. And then I'm going to show you the state transition network that we wrote in order to define and declare this and discuss it with our client. So here's a quick video.
The House of Music Vienna is a museum documenting the city's rich musical past, present and future. It is located in the heart of Vienna, Austria's capital. Its third floor contains 2 exhibits designed by our research group. One of them is Personal Orchestra. This system lets you conduct the famous Vienna Philharmonic. Entering this room, you find yourself in an environment reminiscent of a classical concert hall. On a large video projection, you can see and hear the orchestra rehearsing. Reading the one-sentence instruction on the screen, you walk up to the conductor's podium, pick up the baton, and press the button on it. This baton is all you need to use this exhibit. Moving it up and down and pressing the button lets you select your language. The next screen explains how to conduct and lets you select a piece. We will choose the Anna polka. Now the orchestra waits until you start to conduct. The size of your conducting gestures determines the volume of the orchestra. Conducting towards individual instrument sections raises them above the rest of the orchestra. But best of all, the orchestra follows the tempo of your conducting, using a special algorithm to change audio and video speed in real time without changing the audio pitch. However, if you conduct too fast or erratically, the orchestra will stop playing and complain.
Ihre Schlagtechnik ist ja völlig unprofessionell. Das geht überhaupt nicht. Das erinnert mich an ganz alte Tage an Dirigenten, die überhaupt nicht dirigieren konnten.
But if you conduct well enough, you will be rewarded with a big applause and your players raise themselves. After that, you can pick up a certificate at the museum shop to show that you conducted the famous Vienna Philharmonic Orchestra. This way, Personal Orchestra lets anybody experience what it is like to conduct the Vienna Philharmonic, and that conducting is much more difficult than it seems.
All right. So what you've seen is basically represented in this state machine here. And this is too small to read, so we're going to zoom in on it so that you can, but I wanted to give you the overview of it first. The notation is done in a way that there's a state name inside the box, and above and below, we're going to see these like what the user does, and then a slash, and then what the system does in response. And next to some states, we've written down some comments to explain more what the state is about. So here's a zoom in on the first part. As you can see, the program starts, that's the external event. And as a response, the system starts the showing the rehearsal video loop. And it starts doing that video and then enters the state intro loop. This stays and it keeps looping the video, right? So lots of things are happening. It's playing back the video, it's restarting it when it's over, etc. We're not modeling that in this view here. When the baton button gets clicked, when the user is doing something, somebody walked up to the exhibit, then we start fading the video wherever it is currently is. We stop the video and fade it to black so that the system transitions out of the introduction state and into picking a language. And that's modeled here. We start the video fade, that's the event, that's the reaction of the system, and enter a state in which the intro loop video is faded to black. That only takes a fraction of a second, but it's its own state. And when that is complete, we then switch to a new screen that is the language selection. You can see we could have saved ourselves modeling that this intermediate state here, but if we had, then we would have no good way to talk to the customer about, do you want this transition to actually take some time, or do we directly cut to the language screen without a fade, right? Or how long should it take? These kinds of things would kind of disappear from the discussion if you didn't model this explicitly. And in this language choosing section here, the user picks a language, they move up and down, we highlight the right language. We don't talk about any of this in this modeling level here, but we do talk about if the user clicks a button and picks a language, in which case we move to selecting a piece, or if the system times out, because it could be that a user just walks off and we want the exhibit to be ready for the next person to be usable. So after a while, we just go back to the rehearsal video if we don't detect any input. If the user has picked a piece, we then look at, did they actually pick a piece, which takes us to the right-hand side of this graph, or did they ask for the information page, which is another button on that screen. And if they clicked on the info page, then we show that and wait for a button click or a timeout, and then we go back basically to the earlier screen that you've seen. But if the user picked a piece, we wait for them to start conducting, waving the baton up and down, and then we start the audio and video. And this leads to this conducting state here, which of course is super complex, right? There's amazing stuff going on. We're tracking the baton, we're modeling how fast they're conducting, we're stretching the audio and video to match that. And there's lots of this is the most complicated part of the software. It's modeled in a single state, right? Because this, from an interaction point, to model the entire user experience of encountering this exhibit, this was all we needed to know about this. There's only two things that can happen to get out of that state. You mess up, or you're good enough to conduct all the way to the end. If you mess up, we take you to a little complaint sequence that is played back. Again, that's a short video clip. And after that is over, so here's an example of a trigger that actually just comes from the system, right? When the complaint video has been played in full, it's not a user action per se.
we go back to the piece selection screen. If, on the other hand, you conduct it correctly, we take you to the congratulations page, and we wait, and there's also a little timeout here, and that would then take you back to the initial screen of the orchestra rehearsing again, and you can pass the baton on to the next person. So, as you can see from this, this is how you can use a system like a finite state machine to model a fairly, complex interaction. And some of the discussions we needed to have with the museum, like what happens if I fail in conducting a piece? Should I automatically be taken back to restarting the same piece? Or should I get back to the selection screen because maybe I want to pick something else because I failed in conducting the Blue Danube, so maybe I want to try, the Radetzky March or something. These were the kinds of discussions that we wanted to have with our client, and that's why we modeled the system at this level of abstraction. This was in 2000. Let's forward a few years. This was in 2010. We did an exhibit for the German-Chinese pavilion at the World Expo, the Weltausstellung, I think it's called, that was taking place in Shanghai that year. And this exhibit called Silhouettes let people sort of create their own virtual neighborhood out of trees and water pipes and houses and so on by gestures that they did in front of a screen. And here's a little video that again shows how this interaction works. And then I'm going to talk you through the state machine that we built in order to discuss the design.
Die Möglichkeit selbst, unsere eigene Stadt zu bauen. Wir werden unsere Stadt gemeinsam in der Gruppe 16, das bei uns hier erzeugen, eine kleine Stadt findet. Und es funktioniert in 4 Schritten. Zunächst macht ihr Häuser, dann Strom, dann erzeugt ihr Bäume und dann erzeugt ihr Wasser für die Bäume.
是自己建造自己的城市，有房子、电、树木和水。
Um die ganzen Sachen zu erzeugen, benutzt man seinen eigenen Schatten, so wie beim chinesischen Schattenstil, ganz traditionell. Das heißt, ihr gleich anfangen zu spielen, bewegt ihr euch hin und her und erzeugt das nächste Haus.
是用自己的影子盖一下房子，看到了吗？
Machen wir große Häuser, kleine Häuser, ganz breiten, wie auch immer ihr wollt.
还有oder你把我说。
So, jetzt hier weiter, hier geht man rein, alles. Das soll ja auch nachher.
就是你们的房子到时候要听那个主讲讲话哈，所以安静一点。
Ein Haus braucht auch Strom für die Beleuchtung, deswegen müsst ihr jetzt die Verbindung vom Licht.
现在是用电连起来。
Je länger ihr das verbindet, desto mehr Lichter gehen an und aus.
时间连起来越长，灯亮越多。
This was placing electricity lines in our virtual neighborhood.
Als nächstes sind die Bäume dran. Wir wollen ja auch noch ein bisschen Grün in der Stadt haben. Wie bei den Häusern wieder. Ihr könnt verschiedene Arten von Bäumen machen, auch Tannen oder Laubbäume. Ihr könnt auch ganz kleine Bäume machen. Sehr schön. Seid schon wieder eingefroren? Perfekt. Das letzte, was noch fehlt, ist Wasser für die Bäume, damit
现在是水。
This required people to hook up those virtual pipes.
Und nach rechts mit.
往上，往上，往上。
Dann habt ihr ganz viel Wasser drauf.
自己要看自己的房子，自己要看自己的房
Quadranten. Dieses Viertel könnt ihr unter der Nummer da unten 3537 im Internet nachgucken. Gleich beim Rausgehen bekommt ihr einen Kühlschrank-Pin, auf dem die Nummer auch nochmal eingetragen ist. The virtual city was basically put online and was something that people could then, access online in a SimCity-like environment. Okay, turn off the. There we go. Great. So again, how do we model this in a state machine? Here's an example of the overview of how the system worked. That you can see here. We had so we had 16 screens. These were 16 full resolution projectors, a major setup, and lots of computers that were driving them. And there was a game server that was driving the whole game, that managed the state of the game, and that was basically controlling all these extra game computers that were running the individual screens. And then there was a hosted web server in behind, and a variety of other things, a photo computer and a giveaway computer, etc. But the SDN is interesting. I'm not going to go through everything in detail here. You can take a look at your own time if you want to see more about it. But I want to show you how we model things. We basically had a state in a box here, and that would could go, for example, after a timer to another state, or it could be going through an event that the user triggers. And so this was basically here on the left was saying in any state, in any of the states, a timer would take people to the next state. So it would always advance to the next one. But the game master, who was off to the side, could pause the game if there was a complication because a group didn't understand what's going on. They could stop the timer and then basically press a button to move to the next state, right? If somebody had a problem with the game at a particular point. And so what happens is basically, for example, the initialization of the system would turn on the spotlights on every person's position. And when that's done, then it would ask people to please move up to the system, like to step up to the into the spotlight and do their start doing their gestures, play corresponding sounds, and then the game master presses start game on their little game console off to the side, which shows the welcome screen. And after a timer, it asks people to pose for the buildings. It turns off the spotlights because now people are standing where they're supposed to stand, so we don't need them anymore. And then when this is counting down, this is after a timer, the countdown happens, and then we basically take the picture and show the result of the building, right? And this is repeats then with electricity, trees, and the water, right? In the end, you get the city displayed, you get your full results shown, and then after timer, a state that we called please leave, which was saying like, make room for the next group of people. And that goes also back to the then please move up. This was, so you can see this was like a Disney ride, right? This was highly tacted, second by second, because we had to get hundreds of thousands of people through this exhibit in the few months that it was open, because it was very popular. And so to give you another example here, each of these things had a lot of smaller details, right? So with another more detailed SDN, we could model things like, what's happening in the electricity posing state, for example. We need to send the state over to the floor lamps. We need to display the shadows, then send a feature to the server, receive any scores, send the scores over. And so there was a lot of stuff going on in each of these things. So you can zoom in on that state diagram and see more details on things. But also, if a computer lost a connection to the server, then that we could react appropriately and then reconnect automatically, so that the system would always sort of repair itself. And now the most interesting storyboard was probably the game one. This is a great example of how we as computer scientists work together with visual designers and architects and the client to describe the whole experience and all the different facets. So on the left, you see the visuals that the end user would see on the big screen. Then we have a column that describes what's happening in that state. Then we have a column that describes what the server is doing
in which state it is and what kind of actions it has to do, what the controller that is running the server is doing, and then we have the client and the lights that are being controlled in the environment being driven as well. And here I don't really need to go through all of this, but you can see that, for example, let's go a little bit into this here. This is the, for example, the building posing example, right? It tells people what to do, and the building posing is running here on the server, and the clients are waiting for this to happen, and then get a message from the server, go to the state building posing, and then they do this and they do that, etc., etc. So it's very detailed, and then in comes the countdown indicating that the shadows will be frozen and flash to grab a picture, and then it goes to the next one, right? And this goes on and on for all these tree posing and water posing, and then of course showing the city as a result, and giving people the full result of what needs to be displayed, and then kicking them out to make sure that the next row of people can walk up to the exhibit. Okay, so an example of a more complicated multi-computer interactive experience, also modeled as a collection of state transition networks. Now let's take maybe just the hierarchical STNs, and then we'll do a little break, because that is, I want to wrap up the STNs because it's one topic, and then we'll take a short break after that. One of the things that can make STNs difficult is if you have too many states, of course, and too many transitions and too much detail. A simple way to fix that is to make STNs hierarchical. That doesn't increase their expressive power, but it makes them more convenient. How you can do that is to use the start and finish states as sort of glue points, where you can take an STN for a subdialog, like the one that we just saw, the circle and line one, right? This was the graphics submenu. And you can take these and glue them into a larger STN, for example, the whole application in general. To the right here, we see an example. Remember the circle line submenu. It started off with this graphics menu pointer, and it ended with a finish state. And that whole thing could go into this graphics submenu here. So the moment somebody selected the graphics menu, then this thing could pop up and say, well, you can draw a line or can draw a circle. That's all I have for you in graphics. And when the user does any of these, ultimately it will finish, and then we'll actually take the user back to the main menu. And there would be other submenus for the text options and the text commands that the system offers, and the paint commands that maybe this app is offering. So we can specify a whole application and a whole system in that way, but it doesn't add anything theoretically to the power of what we're modeling. It just makes things a little easier to handle. So how would you use STNs in prototyping? As you saw, it's a good idea to, if you have a dialog sequence that the user is taken through, to model that as with a simple STN. It's very straightforward. Create one UI snapshot per state, label it with the name of the state, give it a self-speaking name so that everybody understands what's going on in that state. You can use the sketch. You don't have to use a screenshot. You can use a sketch if you're still at paper prototyping. And it's always helpful to make the state diagram with a little bit of space to the side, where you can actually add annotations, explain things, include maybe extra buttons that simulate an action of a user, which may not correspond to a simple click on the current screen. And when you walk users through your paper prototype, you can actually take out your STN and use it as sort of a cheat sheet to tell you what needs to happen, where you need to go. Because remember, your paper prototype is dumb, right? We've done that. It doesn't know what to do next. You need to drive your paper prototype, and your STN can be your script in order to understand how you drive your paper prototypes. As an alternative, of course, you can also let the computer run the STN to basically help you execute the prototype. And this can be done. We've seen examples of this earlier on with Keynote or PowerPoint, for example, as prototyping tools.
Let me show you an example of how could be how that could look. So here, for example, is a way in which the graphics menu here is being integrated into the main menu. We can see them both here again. This is the section that sort of is represented as the graphic submenu up here. And if I now wanted to actually build a simulation of my graphics app, right? I'm inventing Photoshop, right? And I want to show an early simulation of how I imagine this amazing graphics tool to work. I could do that by using this notation and fleshing it out into a little prototype, and use the state transition network to drive, basically to include the logic, the dialogue logic behind my prototype. We've done this here. This is adopted from a prototype that Alan Dix and his colleagues actually provided in their book, which you can also download, but it was using HyperCard, a super old tool by Apple that lets you model basically stacks of pages that you can click through and link via buttons and other commands. So it's a bit like, you know, an early version of, if you want, you know, Keynote or a PowerPoint in a way. So here's the simulation of that, right? So imagine Ollie just came up with this amazing idea. I want to make a graphics application. This is how it's going to work. It's going to have 3 menus: graphics, text, and paint. We saw these earlier on. And I've already doodled a little bit of stuff here so that the user can imagine that there's, you know, that they're doing a drawing. And currently the system is in the state of the user, you know, that we call main menu, which is the default state the system is waiting for stuff in. Now, if the user picks one of these 3 menus here at the top, then we will enter into the corresponding submenu, right? Because as you saw here, main menu will take you to graphics, text, or paint, right? One of these 3 submenus, right? So we're going to enter from the main menu into a submenu. And this here could be, for example, the graphics submenu state, from which we can then pick circle or line. So let's do this. Let's pick the graphics menu, because that happens to be the one that's implemented in this prototype. As you can see, because now the pointer turns into a little hand, I haven't implemented anything between text or paint here, right? This doesn't exist yet in the simple prototype. So I click on graphics. What happens? My prototype now moves into a new state, right? Driven by the state transition network that we've modeled behind it, basically. And we've modeled the state transition network simply by putting links into this PowerPoint or Keynote presentation here that take us to different pages in our presentation. That's how we modeled the SDN. So I click graphics, and up pops a menu. Wow, right? So we've now opened up a menu. We are now in the graphics submenu state. And in that state, we can then take either the circle or the line as a concrete command, right? Now, if I click on circle, for example, as you can see, again, line isn't implemented, only circle is implemented in this prototype. So I need to click on circle. If I do this, I'm now in the state circle 1. I think, Ollie, by the way, I think we should probably fix the menu state, right? That should have updated to the graphics submenu there. No problem. But now we're in state circle 1. And in circle 1, now comes an interesting problem. I'm drawing here, or Ollie is drawing a simple prototype of his application. His application cannot draw circles yet, right? It doesn't have the logic yet. It hasn't been implemented yet. We just want to simulate this, right? So how do we do this? Well, we just say, well, imagine that you are now clicking somewhere on the screen to define the center of the circle, right? So the prototype says, click this button, the blue one, to simulate a click on the drawing area, which will define the center of the circle that the user draws, right? All right, so I can't actually click into this thing, but I can click on this button, which simulates a button click in my prototype, right? That's what this is meaning, because the prototype doesn't know how to draw, right? It's just a bunch of still images, really, that we're showing you here. So we do this, and now imagine the user has moved their pointer to another position and has created this rubber band. We're not simulating the whole rubber band expansion here, right? We're just saying this is the next interesting moment in our prototype where the user clicks again on the circumference of the circle. So let's simulate that by, again, clicking this blue button here. And if we do that,
the circle gets drawn by the tool, right? And now, when we're done with that, we can then step back to the main menu, because that's where, after the command is completed, our system, which, you know, this is what our STN tells us, our system would go back to the main menu state. A little question of understanding here. If I click main menu here now, what's going to happen on the drawing area here? What do you think is going to happen? Is anything going to happen? Yeah, Tobias, go ahead.
I guess the circle will disappear in that case, even though it shouldn't.
Exactly. Circle goes away. I click back to main menu. Circle is gone. Why? Because I'm back in the main menu state, right? I've circled back, sorry for the pun, to the main menu state, which was the original state that my demonstrator started in. So this is important to understand, right? The simple simulation doesn't actually have the power to create the state of drawing 1 or 2 or 3 circles above each other and remembering where each is and so on. That none of that exists, right? It's just a bunch of screens that we've hooked up with each other so that they look like what you would experience. Okay. So as a result, you know, you could then, you know, keep stepping through this thing forever if you wanted to. I'm not going to do that. I'm just going to go to the next page here. But this is basically how this thing works, right? These are all just individual pages in our presentation. So what do STNs offer us in terms of what we can do with them? First of all, STNs, as you know from theoretical computer science, are great in verifying completeness. Completeness means if I'm in any of the states, there has to be some way to get to every other state, right? However convoluted and complex it is. If that's not the case for any combination, then we have an area in our STN that basically isolates people from using, you know, they get stuck in a part of the STN, right? That isolates them from using the rest of the STN. So that's something you want to verify, and you can easily verify that with, you know, formal methods for state machines, for automata. Another thing that you can verify is, are all the possible actions actually covered in every state? Meaning, does every state tell me what to do if the user does any of the things that they could possibly be doing? By default, if I don't specify a user action in my STN as a possible transition out of a state, it means that I should ignore it, right? The system should ignore the user input. And a third thing you can verify is, how easily can I get from A to B? Like how easily can I actually get from one state to another one? Is it as easy as it should be, or is it maybe unnecessarily complex? Does it take too many state transitions to get to from A to B for an action that I maybe need to do a lot of times? The other thing you can verify is it possible to get back to the previous state? This does not mean undo, because undo would, again, is more complex, but undo would mean to actually undo the consequences of what happened in our program in the world around us. And, you know, sometimes if I burn a CD, I can't undo that, right? But I at least want to be able to get back to the state in the system that lets me maybe, I don't know, burn another CD, right? To retrieve my previous state. And finally, we also have the option of checking on whether some of the states are things that maybe you don't want to get into too easily. Are there situations in which it is tempting to fall into a particular state? So I said whether we can check completeness, and that we can find out whether we maybe missed something where a user could do something in an interface that we haven't specified how to react to. Let's take a look at an example here. We actually have an example in the very graphics application that we modeled here.
So you may remember this was the the way to draw a line or a circle, and we clearly specified that people can draw, for example, a line by first selecting the line tool, then clicking on the first point, and then ultimately double clicking to finish drawing that line, right? So that's great, but what is supposed to happen if I issue a double click somewhere here in the circle tool, right? A user who's gotten used to completing their lines with the double click might think that they need to complete their circle with the double click too, so they might double click here. And whether that's smart of the user or not is not of interest. The question is, we didn't specify what should happen if the user double clicks in circle 2. So by default, for the implementation, that means ignore that input, right? Double click doesn't have any meaningful effect. And this is a design question, right? We could say, well, yeah, double click doesn't make sense here. We don't want it to do anything, and then that's fine. Or we could say, well, that could actually be, we should accept that because it's, they got used to this from completing the line. So let's use a double click also to complete drawing the circle, right? Or maybe it has a different meaning than just clicking once. I don't know. There's all kinds of options. These are design options that you need thinking about in the user interface design process. And once you've come up with a solution, you need to specify it. Oh, how does the system know if it's a double click or just 2 singular clicks? Gabriel, that's a good question. Typically, what happens in a system, we talk about this more in DIS2, but what typically happens in most systems is that as clicks come in, they are being processed and aggregated. So if 2 clicks happen in rapid sequence and the timeout between those 2 is typically a variable that the system defines, sometimes the user can even set it and choose how quick double clicks should be happening, then the system basically takes the 2 individual clicks off the event queue and replaces them with a double click instead. So it's a question of processing the incoming event queue, looking at the timestamps of events, and then basically reacting to that by replacing single clicks, 2 single clicks with a double click. Now, so what you can see here is that we didn't say what should happen by double clicking in circle 2. And in fact, that's true for all the other states, right? We never specified what a double click should be doing. So by default, that would mean that it gets ignored, right? Which could be confusing. And if the user double clicks to select the menu, for example, technically that would probably mean that we need to throw it away. So this needs thinking and needs to be specified. Reversibility is another one of those. I said that we can check whether people can get back to the state they were in before in the user interface if they ever sort of made a wrong move, right? They just took a wrong turn. They want to get out of a function that they didn't mean to trigger. This is not necessarily an undo, as I explained before with the CD burner, but it is a way to get back to the user interface state that we were in before. And as you can see here, if the user has selected the line tool, what we can see thanks to our SDN modeling is that in order to get out of the line tool, they do actually have to click at least on the first point, because there's no other way to get out of this here. They do have to double click to actually draw a line. And only then they end up in the finish state, which is our connection point from the submenu from this sub SDN into the main SDN, which would then take us automatically back to the main menu, right? This is what the finish state then leads to. So we're back at main menu state. And from here, they would actually have to select the graphics menu one more time. And then they would be back in the menu state that we talked about here. So what we're seeing here is that the SDN is making it obvious that we need some kind of escape functionality that you can cancel an operation that you started, right? Because nobody wants to go through and draw a line just by mistakenly picking, the line tool, obviously, right? That would be bad design. So it's already beginning to be useful for us because we can visualize
the usability issues and clearly show them and explain them to everybody. And it's not just, you know, waving your hands around and saying, oh, this is kind of difficult to use. Dangerous states. I gave an example on that as well. And I said that, you know, we can identify dangerous states. Here's a concrete example. Let's imagine you've got a word processing application, right? You know, a text editor. And let's also assume that this text editor has different modes, right? It has sort of like VI, it has a mode in which you, you know, edit, and that's the edit mode here on the left. And it has a mode in which you can issue commands, which is the menu mode, right? And let's say you transition between those two modes, pressing the F1 function key, right? Just for the sake of argument. If I press F1 to get out of edit mode and to menu mode, then I can then press exit and save, and that's fine, right? That will save my changes. I could also, you know, an escape does not change the mode, so it stays basically inside the menu state. It would also, for that matter, stay in the edit mode. But there's one extra thing. If we do press escape, the editor is written so that it resets the autosave flag. You know what that means, right? You've loaded up a file. You didn't mean to change it. You started making some change. You realize, oh, I didn't actually mean to change this. In this case, you would hit the escape key and say, consider this file unmodified. Yeah, don't autosave this. Okay. Now, this is, first of all, this can lead to dangerous states. Why? Because if I were to exit without saving, I lose changes. And if that's intended, great. But if that's unintended, not so great, right? So far, we do have dangerous states, but they are protected, right, by the escape key. What do I mean by that? Well, the blue states are you could call them save states, and the red ones are the unsaved ones. The blue ones, I'm editing a file, I'm moving into the menu, I'm going back to editing, moving back to the menu with the F1 key. At some point, I hit F2, I exit my program, it saves, everything's great. If I load a new file, I'm in the red mode because it's there's nothing to save, right? No change. The buffer of the file is unchanged. There's no autosave to be done. But as soon as I enter any text in there, I move up into the blue edit. So I'm in safe space, right? I've made some changes to the file, and those changes that I make automatically move me into the blue state, in which if I were to exit with F1 into the menu state and then exit with F2 and close the application, it would actually save. Great. I can get back into the unsafe area down here by pressing escape, right? If I press escape in the menu state, we said that it actually stays in the menu state, but it resets the autosave flag. So it basically says that it considers the file unchanged, meaning I could now exit my program without it automatically saving my progress. And again, that could be intentional, as we said, and it's well protected because I need to actually hit the escape key in the menu state and then press F2 to get out, right? As soon as I press the escape key and I go back into my file with F1 and do more changes, the changed flag would be raised again, the autosave flag would get raised again, and it would save again. So F1, F2 is an exit with save. F1 from the edit mode, pressing escape, and F2 is an exit with no save, right? But that sounds on, and now we get to the interesting things. So the on the old keyboards that were around when this application was designed, again, this is a hypothetical experiment, right? So, but this keyboard layout actually existed. On old keyboards, the function keys were off to the side. Remember the Alto and the Star that had their like dedicated buttons for like copy, move, etc. For a while, function keys would still be to the left of that main keyboard on early PC keyboards and workstation keyboards. So here, everything was still hunky-dory because I could press F1, F2 all I wanted. If I really wanted to basically get out of this, into the dangerous state, I would have to hit F1 to get into my menu state. Then I would have to have escape over here. And then I would have to hit F2. And that's clearly something I don't do by accident, by just slipping on a key, right? Not happening. But now comes the issue. The new keyboards, and that's probably what you have in front of you on your home laptop too, have the escape key right next to these function keys, right? And with that, we now end up with a dangerous system. Why? Because the sequence F1 to get into the menu state, escape to turn off the save flag, and F2 to exit the program are actually extremely close together. I could hit the F1 key, just slip on it a bit, hit the neighboring escape key with the F1 key, and then press F2. Maybe that becomes my standard routine. F1, F2 is menu exit, right? That's like your standard keyboard shortcut to leave this application with saving. And you do it so quickly that it becomes second nature. And at some point you slip and hit the escape key in between, and boom, before you know it, your GOMS sequence is still running, right? You haven't even stopped to check what you're doing. You've suddenly thrown away your progress. And so that's what you don't want to do. And again, this example was not about whether it's a good idea to design an application that way. My example was trying to show you that by having the state transition network as a notation, I can talk about these issues and I can visualize them and make them apparent and put them up for discussion in the design team. So that's the idea why these charts are really helpful, because they provide an easy way to analyze and visualize and discuss these problems. There are more properties, especially properties of transitions that you can check in STNs. One is determinism, right? Deterministic automata are those that will not have more than one way to, more than one transition out of a state for a particular trigger coming in. And if you have a state transition network in which you can have you're in a state and a particular event happens, and there are more than one exiting arrow that fit that event, so that could possibly be used to exit the state, then you have a non-deterministic automaton. And that can be right sometimes, right? Maybe if it's a game of luck, if somebody presses a button and the button should, in 50% of the case, it should tell them it's a virtual coin toss, heads or tails, then of course you want the button to sometimes lead to the heads and sometimes lead to the tails. But it's not that often that you want this non-deterministic behavior in your system. Now, if you want to model this kind of deterministic, non-deterministic behavior, then it's probably a better idea to go with a production rule system, right? In which production rules have basically the non-deterministic nature built in, because all the production rules can fire at any time, right? So they are all loaded, and you just need to write two production rules with the same incoming events, and then they will both possibly fire. Another thing you can test is what's called nested escapes. So nested escapes means if I press escape to, for example, get out of a state transition network, I can hop out into the parent state transition network, especially with hierarchical state transition networks. And that's something, again, that you can model quite nicely. Also, consistency is very interesting. Let's say you've got lots of transitions in your STN that say that the trigger is the user pressing the command key shortcut Control P, right? So they press Control P, and as a result, you end up in a new state. You can check whether all these transitions, which are easy to find, actually lead to something that semantically is related. Does it always print something, for example, whether you're in a
word processing system or whether you're in a graphics application. If you're modeling a whole system, you can verify your consistency that way. So does the same action of the user have a similar analogous effect? Also, modes and visibility are quite nice to model with this. We've already seen an example with this F1, F2 escape disaster. This was in part because of the system having these different modes, right? Having the edit mode and having the menu mode. And so modes are also nicely modeled because you will find that you need to essentially double everything when the system is in one mode versus the other mode. And for each of these two modes, you need to specify what each action does. And if they do different things in the two modes, then that hints at a mode issue with the interface, right? Because that's something that the user might stumble over when they press a button that they expect to do something and it does something else because the system happens to be in a different mode. Okay, let's do a little in-class exercise here. This is a fun one. So get out a piece of paper and a pencil or pen, and I want you to draw a state diagram for a very simple dialog box. Now, we are not concerned about how we exit this dialog box, about the close buttons up there. You know, ignore the stuff up here. We're really, this is not important. We're really just interested in what's inside this, red dotted line here. We want to model. I mean, this state block can obviously be in a couple of different states, right? It can be bold, can be checked or not checked. Italics can be checked or not checked. Underline can be checked or not checked. And I would like you to draw a couple state diagrams, and we'll start very simple. I would like you to first draw a state diagram just for the bold checkbox. And these other two are gone, right? Those don't exist, italics and underline. And you just have a box there that you can check that says bold is on or off. What's the state transition network for a dialog box with just this one checkbox? It's very simple. I'll tell you this.
Yeah, I would just, simplistically, I would have the state at the beginning would simply be not bold. And if you say turned on or like ticked, whatever, then you go to bold on. And then if you tick again, you will just go back, and that's it. And you can you can have both states as the end state.
Exactly. I can actually show this because that I think is pretty straightforward, right? We have, let's say, regular text style, which you call non-bold, right, Marco? And then if I check the bold checkbox, which is indicated here by this word bold in apostrophes, so I'm toggling the box. Then I enter the bold state, and if I'm already in the bold state and I toggle it again, I get back to regular style. Easy enough. All right, now let's add italics to that. So go ahead and what would you need to do to extend your STN to also include italics? Think about that for a second, and Aaron has an idea.
Yeah, in this case, I guess we need 4 states. So the basic regular state that we had before, and then the bold case, the italic case, and the italic and bold case.
Very good, exactly, right? So, and the connections, of course, are now something like that, right? So we've got our existing bold italics remains, our existing bold sort of STN remains, but we kind of duplicate it and say we need this again, but this time with italics on, right? And then we transition from our first STN subgraph here to our second STN subgraph by hitting italics one or the other way, right? Okay, so now we have bold to be turned on to basically every time I check bold, I transition from left to right, right? And every time I hit italics, I transition between top and bottom. Great. Now, add underline, right? That's the third option here. What does that look like? Felix, is that your old hand or is that a current hand?
Yeah, both. I think,
okay, good.
there are now 8 states, one for the regular style, then one for each option only, then one for 2 combined, and one for all 3 checked.
And what do the connections look like? Like, how would you visually do that with what you already have here? How would you draw this?
Yeah, I would simply draw the states, and then the arrows would get a little bit more complicated from there on.
But yes, they would get a little more complicated. Nikita, how would you draw this?
I think it would look like a box, like in 3D maybe. So like all arrows going in the back.
Yeah, so kind of like this, right? Yes. Exactly. Thank you. So we now have basically, and notice the regularity, right? We've taken our initial bold thing and we've duplicated that automaton down to here to the bottom ones and connected it with the second option in the second dimension. Then we've moved into the third dimension now, again, duplicating our entire existing automaton and connecting between the 2 dimensions with a new toggle word, which is underlined in this case, right? So this now covers all the 8 combinations of bold, italics, and underline being on or off individually, which is, of course, 2 to the power of 3 for 3 options. So 8 different nodes. And if you were now to add something like capitalized, so all caps or non-caps, to this as a 4th checkbox, just in theory, what would that look like? Yeah, Marco?
Yeah, of course, like now making it as a 3D model is different. I mean, difficult because you would need, like, let's say a 4th dimension to present it. But basically what you can imagine is that you just basically always have to model the combinations that are possible. So it's always like if you have, well, let's say here 3 possibilities, then the combinations that you can have is 2 with exponent of 3 powered by 3, for example.
Yes.
So of course now to model it is a 4D model would be difficult, but it always gets doubled with every possibility.
Precisely. So that option gives me the unique chance to say the word that I always love to say, which is we get a hypercube, which sounds so amazing. So that's a hypercube, and that's a pretty lame drawing of a hypercube, but yeah, Ollie ran out of the 4th dimension while he was sketching it, I think. So this is as good as it gets in 2D, I guess. So what you can see here is, again, we took the whole box, we duplicated the whole box, right, with all the 8 nodes, and we connected each node from the left-hand side to its corresponding node on the right-hand side. And all these new transitions that we've added now are the ones that were capitalized as turned on or off, right? Okay. You see the problem, right? State explosion. Adding a single additional checkbox in our dialog there means that we double the number of states. And in general, that means that if you have 2 STNs, and this is important, 2 concurrent STNs that are running at the same time, that are both active in a way, with n times n or m states, then you get a new combined STN that has n times m states. In our case, n was always equal to m, and it was always 2, and we just kept adding, right? 2 by 2 by 2 by 2 by 2. So what this means is that as the state explosion is happening, your STN begins to hide the very clear structure of the dialog, right? Because, I mean, the dialog is super simple. It's 3 checkboxes. Each can be on or off, right? This should be, and this gets lost if you look at this hypercube. It's way too complex to quickly visually parse what's going on. And this is especially problematic with today's graphical user interfaces, because they consist always of lots and lots of different options of things you can do in parallel. And all of these would have to be modeled in any combination of sequence that people could think of, right? So that gets messy. This also gets messy if you think about other, fairly standard dialog requirements. For example, you might say, I need to get out of this drawing command, you know, the line command that we talked about before I complete it. I just hit the line tool by accident. I want to turn it off. I want to get out of it. We clearly need a way to do that. And you might say, well, hit the escape key anywhere before you complete a drawing tool command, like, you know, finish your circle or finish your polyline. And escape just means, you know, I cancel the drawing command for you and I take you back to the state. That's a great idea, right? That's a great design. But imagine what that would mean in your STN. You would actually have to hang a separate, you'd have to hang a separate escape function of every single state in your diagram, right? Or let's take help as an example. If you want a help function that basically always provides help to the current, about the current function that you're doing. So if I hit help while I'm drawing a circle, I get help about the circle tool, which would be useful. That means that we need a separate little help dialog hanging off of each single state, right? Because it's going to be help relevant to that state. We can't just say, go to help globally. And then how do I get back, right? How do I get back from help to what I was just doing? In order to do that, it needs to remember that I'm in that state. And it can only do that by adding a substate specific, you know, a sub STN specific to each state. So it gets very messy, right? So that's the problem with escape and help options. Escape could be modeled as a special second finish exit that's active throughout the subdialog, and help can be modeled as a little subdialog hanging off every single state in the STN, but it does get messy. Here's what this would look like graphically. So maybe first let's take a look at the escape key here on the right. You enter the graphics submenu, and here's a shorthand visualization for this, right? This is not actually showing the fact that this escape option would have to hang off every single node inside the graphics menu, right? We're already cutting down on visualization here, saying, okay, escape within this graphics submenu, if somebody in any state within this graphics submenu, that's why this arrow goes out from the box as a whole, says, if you hit escape anywhere in the submenu, please take the user back to the main menu, right? That's what this is saying. Whereas if the user reaches the, you know, the finish state in the submenu, then finish the command normally by drawing the line, the circle, the whatever. Or here's the help subsystem action, which is actually, you know, maybe a little subtle, right? This may be something easy to miss. You might say, well, I can just go from circle 1 to the help system, right? And I can go from circle 2 to the same help system. Why not? Maybe I could even mark the transition to say, go to the help system, but tell the help system to show the help for, you know, circle 1 state or circle 2 state or line 1 state or line 2 state. That's all nice. But once you are in the help subsystem, how do you get back to the right command that you came from? Right? It's impossible because your STN cannot remember that distinction, because the only thing that remembers is that one state of the currently active state in an STN. That's the only thing that an STN remembers. One circle, one state that is currently active. That's it. It doesn't have any more way of handling history or something like that. Then you would get to, you know, stack automata or something like that that can have additional information stored. So this is important why we can't just use one single help subsystem box here, because we need to know that this is a help subsystem that is designed to go back when the user leaves it to the circle 1 state. And this is the help subsystem that takes you back to the circle 2 state, if that's important for your interface design. You might say it's not important. I can, once the user pressed help and they come back from the help system, I'm just going to throw them into the main menu state and they have to start from scratch. It's a decision you can make, but you need to think about the usability implications. So what I'm trying to say here is STNs are great, and you've seen us use them for real-world projects, but they do have some drawbacks, and you need to be aware of these, and especially the state explosion. Now, how can we handle state explosion better? Petri nets, another student favorite from your theory lectures. Petri nets are actually a better approach to model dialogues that have more than one state at once. They are not, let me get that out there right now, not better for sequential dialogues and mutually exclusive user interface elements like radio buttons, for example. Not great. But for the example of the checkboxes, Petrinets are awesome. They are a really old formalism to model concurrency, right? This was really one of the key features that Petrinets enable. So I'm sure you've all seen Petrinets in your studies. I'm just going to reintroduce them very briefly to refresh everybody's memory of how they work and maybe introduce the kind of notation we're going to be using in our short demo here, in our short example. So Petrinets consist of transitions, which are these bars here. And transitions have the property that they will fire when all of their input places are the things connected into a transition with an ingoing arrow. So the circle and its ellipsis here, when all these places have one or more tokens. So if we see a token in each of these input places here, these ingoing places, then the transition will fire, will consume all these tokens, and will put a new token in each of its outgoing places. So transitions, places, tokens, important to remember. This is the logic of how Petrinets work, right? So kind of like a production rule that fires that can fire as soon as all its incoming tokens are fulfilled or available. A Petrinet transition can fire as soon as all its incoming places have a token inside them. Two things to remember here. First of all, we are going to distinguish, and that's maybe unusual from normal Petrinets, we're going to distinguish between your average normal standard place in a Petrinet that basically is part of the state of the Petrinet, whether that place contains a token or not, is one element in the complex state description that makes up the entire description of the Petrinet. And we have elliptical input places, which we squish a bit to indicate that these are the ones which we will place a token into to simulate a certain kind of user input. Okay, so elliptical are user input places in our version of Petrinets. The second thing to remember is a state machine. If you want to say, what state is this automaton in? If you ask your body, what state is this automaton? All they have to do is point to one state and say, that's the active state. That's all, right? That describes the entirety of how to model the current state of a finite state machine, of an automaton. With a Petrinet, in order to describe its current state, you actually need to know about all the tokens that are distributed across the entire network, right? The whole Petrinet may have tokens here and here and here, and the whole of all these tokens in these places is the description of the state of the network. So it's much more complex as a state description than with a finite state machine. And that's exactly where the power is coming from to capture more complex user interface states by putting tokens in particular places, because Petrinets can have multiple tokens in multiple places at the same time. This does not exist with state machines, and that's why they're less powerful here. It's a good way to understand this. Okay. Tokens, by the way, are not preserved, right? It's not like I have a little bag of 16 tokens and those will never go away. No, when a transition fires, it pulls all of the incoming tokens out and it puts one token in each outcoming place, right? So this can definitely reduce or increase the number of tokens that are flowing through your Petrinet. Just be aware of that. Okay. So let's look at what's happening here. Let's say you've got this this sample Petrinet down here at the bottom, and two places already have tokens, but this input place doesn't have one yet. Now the user does something, clicks maybe, and this is represented by a token being placed into this input place. Sorry. This is the moment where the transition can say, aha, I've got tokens in all my input places. I can fire now. And by doing that, it consumes all the tokens
from the input places and puts new tokens into output places. And it happens to be 3 gone, 3 added, but like I said, this doesn't have to be the case. Now, and this is maybe a little trickier. Draw a Petri net for our dialog box. And the very first step is going to be to just, again, draw a Petri net just for the bold statement. Let's just do bold, not even italics. See if you can draw a Petri net, a very simple one, that has the ability to model the user interface state of bold is currently selected or bold is not currently selected. And what your Petri net should have is an input place that represents the user clicking on that checkbox, right? Toggling it. Ideally, you should only need one input place to do this because there is only one. there is only one input that the user can do. They can click the checkbox, and whether they're selecting it or deselecting it is not their option. They're just toggling it by clicking into the same field. So this may be, this may take half a minute to think about this, how you would lay out a Petri net with this style. So we got a bold or not bold, bold on, bold off, basically, other 2 things that can happen to your simple thing. And I'm going to show our graph here again so that you can remind yourself of the notation. And if anybody has a solution, I'll be happy to hear it.
There's a question.
Marco, or maybe you got a solution for us?
Oh.
Okay.
Yeah.
Well, let's hear it. What do you think?
This is how I would think. So of course, for the beginning, I will have this one place where the beginning token enters. Let's say like that, which is the state where you have the regular looks. And then I would have the 2 transitions. No, I'm talking nonsense. No, I mean 1 transition, which would then go to the other state, which would then transport a token, but then that other one would have a different transition, which would then transport to the first place that we had. So the token could go to either ticking the bold, then going to the new place, or ticking again, which is kind of different action, which would then go to the state before. So the token, so you have only 1 token at the beginning, which is at the non-bold, and then it goes either to bold or non-bold.
Yes. Good. Yeah, that's right. Thank you, Marco. I'm going to show our version of this graphic, and I think this roughly matches what you were describing, right? So we've got 2 transitions. That's right. And the state of the system, whether bold is selected or not, is represented not by 1 place, but by the combination of these 2, right? So bold on or bold off. In our particular case, we know that because the way this is designed, there can only always be a token inside the bold on or the bold off state, right? Or place, I should say. So both places cannot have a token at the same time, and there can also not be a token in either of them, right? It's not impossible that both are empty. And how does this work? Well, the moment I press bold here, let me do this maybe. If I press bold, then I would place a new token into this place, right? And at that moment, this transition would then say, oh, now I'm complete. I already had the one from, let's say bold was on at this moment. You're right, Marco, we should probably start with bold off in the beginning because that sort of is the default state to begin with. Ollie, I think we should probably actually maybe change that around to make it less confusing.
Yeah, in this case, that's just the image on the top. That's the reason why. But we can change this, yes.
Okay. And so if the user then clicks bold, then both input places are now loaded and the transition can fire, and it consumes the 2 with a little fire effect. Wow. And
it puts one token. This is an example of a token getting consumed, it disappears, right? It puts one token into the bold off state. And it makes sense that one token disappears because we don't want this user effect. And if this token was generated by a user clicking, we don't want this to float around in the system forever, right? It should get consumed once it's done its thing. And now bold off is active, and we can actually hook the same place up to also the second transition. Or you could have a separate place for this, but this is the more elegant way because there is only one place in which the user is clicking. And now if the user clicks again, obviously, then the token goes up to the top. And you didn't see the other part of this. Okay, kind of mood questions, and I just showed it. But anyway, what needs to happen to make this work with italics as well? Felix?
Yeah, the whole thing can be copied and just
yes,
exchange
exactly.
bold for italic.
Yep. So once we have this thing, we then basically can just do the same thing with italics. And it's important to notice that we now have two independent petrinets, right? These are completely independent of each other, but they belong to the same overall petrinet description of our dialog, because the state of the dialog is described now by the state of all of our petrinet places, right? Where are all our tokens right now? At this very moment, the two tokens are in the bottom state. So this would describe our dialog to be bold is off and italics is off. And now you might say, wait a minute, bold and italics had 4 states in my automata, in my finite state machine. And now I have 6 weird things here. And this looks more complicated than the state machine. And you'd be right? For the two, we're not really getting a payoff. But I'm sure you can see what happens if we now add underlined, right? I think this is too easy to ask as a question. We just add another one, right? So we just get a third of these and put it next to each other. And now we are at 6 of these places plus the three buttons, right? And as you can see, we are going up linearly in the amount of states or places as we add options, as opposed to exponentially, right? Now, if you were to add caps, you would only have 4 of these things next to each other, and nothing would get more complicated. Whereas we are already at the hypercube, with the finite state machine. So, in short, I think it becomes clear that petrinets are not just less effort to draw for highly parallel systems, but also I really feel that it represents the dialogue so much better, right? We have clear places that simulate this is where the user input is happening. You press bold, you put a token right here. You press underline, you put a token right here. And the functionality of the dialog, the semantics of the dialog are nicely encapsulated in these individual petrinets. That's why petrinets are interesting. Okay, now I have to also say, this petrinets, since they are such a much more powerful means of expressing state and dependencies and relationships, of course, are also a little harder to wrap your head around if you don't know what somebody's trying to say with a petrinet. And they're also a little harder to verify automatically, just because, of course, the fact that you now can have any combination of tokens in your various places as a potential state of a petrinet means that you now have an exponential number of states in your petrinet, right? So, for example, actually verifying whether a petrinet is correct and modeling things correctly and has no situations in which, for example, we end up with 2 tokens in both underlined on and underlined off is a little trickier. So this is one of the reasons why neither state machines nor petrinets were adopted as the notation of choice when we came to state charts. But there's a question. Let's see. How can a collection of petrinets be shown as interconnected? Is all 3 a needed proof? Okay, that's a good question.
we don't have a formal notation for this. Basically, if you draw these three Petri nets onto, I will say, a sheet of paper and make a box around it and say, this is the overall Petri net collection for this dialogue, then that's your answer. We don't have a formal way of showing that, because there is really no, how should I say this? There's no formal connection necessary, right? None of these Petri nets needs to know about the others in any way. It's just you as a dialogue designer, you need to know that these three together, now each of them is basically modeling one of your checkboxes. And the fact that all these checkboxes are in that dialogue and can be operated in parallel is something that you would have to basically indicate by grouping these three Petri nets together in a box, or like saying, this is the Petri net collection for this dialogue. Okay, so, but like I said, neither state machines nor Petri nets were picked as the notation of choice when UML was introduced. Instead, what UML uses is a mix between these. It's kind of an in-between version of that combines some of the advantages of the higher expressiveness of Petri nets with the nicer handling of state machines in general for simple cases. And these things are called state charts. They were introduced by Harel, but as I said, UML uses them. And they do extend STNs with three different things. So they're basically state transition networks or finite state machines with three extensions. The first one is hierarchy. So you can put a whole state transition network, a state chart, like the one here on the left, into a box, or all these things here down here into a box with these rounded corners, and that is now a subnet that is hierarchically grouped. And this means that I can draw something like this off arrow here. That means that it is really dangling off every single state inside my subchart, right? So every single state inside the subchart here has an off arrow dangling off it, and that leads to the standby state. The second thing that state charts support is concurrency. With the dotted line here in between, we are indicating that the left state machine and the right state machine are actually running in parallel. I'll go through how this works when I discuss the example in a second. But let me first go over the features that state charts add. The third one that is added is this escape, which is basically what I just explained, right? The off arrow being always active, no matter what state I'm in each of these subcharts here. And finally, we have a history function, which means if I enter a state machine, if I enter two state machines, I need to know now, okay, which one is going to be activated in each of these. We do this by entering the left-hand one with the arrow going here, and the right-hand one gets activated here. But I can mark the start state in the turn on moment with this black little dot here. But what I can also do is I can put an H on this, and that means the first time this state chart, this part of the state chart gets activated, we start at this state. But if we ever leave, for example, because the off button got pressed, then we remember what the state was that we were in. And next time we come back, we actually start again from there. So that's why it's H for history. Let me explain now what we're seeing here. We're seeing here a remote for a really simple TV. This TV only has an on and off button. It has a single channel button that you can use to flick through 4 channels. And it has a simple sound button that you can only turn on or off, like a mute button. And it has a reset button to reset the TV to sort of factory defaults. How does that work? Well, the whole system is a state chart that starts, which is marked by this black dot here, with the standby state, which is basically off, but not completely off. If from here on I press the on button on my remote, that means that I get into the this big state here. This is sort of the on state, which is a big compound state that consists of two concurrent substate charts that are running in parallel. The moment I press the on button, I enter each of these, which means I end up turning on basically this left state chart, but also this right state chart. But the on button only leads to the box as a whole, which means I'm not activating particular starting states in my state charts. I'm just activating the default starting states in each state chart. And those are again marked with the black dot. So if I hit the on button, what that means is sound will always be on, because that's what this state chart starts in when it gets activated and doesn't get told anything else. Similarly, the channel state chart, that is the channel selector, when I hit on, will start the very first time I power up the TV with channel 1, because that's where this start arrow points, but it has an H for history. So next time I turn the TV off and back on, it will go back to the last channel it was on, which is kind of useful, right? So that's a good user interface feature. It remembers the channel I like watching. Now, what about the reset button? The reset button actually doesn't point to the state as a whole, but instead points directly to individual states inside each of these state charts, which means it overrules the default start state or the history function and activates each of these state machines precisely with that state active that it points to. And that's why it's resetting. So if you ever press reset, then it will make sure that the TV is on, which is kind of superfluous because it's also on when you just turn it on, right? But more importantly, it always resets the channel to 1 because it points there. The select button on the TV remote just picks the next channel and goes from 1, 2 to 3 to 4 and back to 1. So that's not exciting. And the off button just works from any state in here, anywhere where I am, whether sound is currently on or off, or what channel I am on, doesn't matter. Whenever the off button gets hit, both of these state charts below kind of go into a freeze state, if you want. They go into a dormant state, and the system as a whole transitions into the standby state. As you can see, while we're in the on state, I can actually both hit the select button to move through my channels, and independently, I can hit the mute button to toggle my sound on and off. This is similar to what we did with our checkboxes for bold and italics, right? We could operate both of them independently in parallel, and that's the power of parallel concurrent state subcharts or subnets that state charts feature, and that they kind of make them a little akin to Petrinets. This is a very powerful and very well thought out sort of compromise for design notation, and that's why UML picked themselves as the standard. And it's good because you can model design decisions in here, right? So it's a design decision that the sound is always on when I turn the TV on. It wouldn't have to be that way. It could also remember the last setting, right? That would be easy to do. Just add an H to this, and then that would mean next time I enter it, just like with the channel, it will remember its last setting. And that's something you can discuss with your users, with your client, with your developers. You can have that discussion in your design team with experts and make the right decision, and then write it down and have it fixed and expressed in your stage chart, rather than the development team at some point later in the implementation making a decision based on what's technically most feasible or easiest to build. There was a question from Obadul Kabir. Go ahead.
Sorry for the question, but by seeing the channel subsection, basically I'm a bit confused about like, is the remote only allows the user to sequentially change the channel, or user can jump from? Okay.
Yeah, that exactly. So that's it's a lame remote. I completely agree, right? You can only go from channel 1 to channel 2. You cannot go directly from channel 1 to channel 3. It's a single button, SEL, that you press, and each time you press it, you get to the next channel. Actually, Ollie, years ago, I think we had a drawing of the remote that somebody created for this to just show what we're talking about. Let's take another look whether we can unearth that, because it might make it a little easier to understand what we're talking about.
Okay, we'll make a note.
All right, cool. Okay, so
now we know how to specify dialogue behavior for the implementation. But we can also use it for documentation, because some of the descriptions are actually great starting points to start a user documentation, right? Similar to the GOMS model. If your GOMS model is really good, then you actually basically have a step-by-step tutorial on how to do every single action, because that's exactly what the GOMS model represents. Especially so if your description uses screenshots of your actual tool in the later stages of your development, and if it is sort of semi-formal, so it's not completely blown out of proportions with millions of arrows and stuff, but it's trying to simplify things and aggregate things in a reasonable way. So our examples of the silhouettes exhibit, for example, with the gesturing thing, I think show nicely how you can use these kinds of notations to create useful documentation. Also, for example, to introduce somebody who needs to run the exhibit into how it works. I want to show you an example of how user instructions often are represented using state diagrams and formal notations, and also how they sometimes curiously leave out things. So here's a simple digital watch, and it has two main modes, right? A time or a stopwatch display. And you can see this has only 3 buttons, right? Button A changes the mode. So if you press time, you press A, you get to stopwatch. If you press it again, you get to time. So it toggles between those two. If you hold down button A for 2 seconds, you get to the alarm setting. If you hit it again, you get to the time setting. If you hit it again, you're back to the main display. Sounds great, but there are a few things that aren't clear here. Why? Well, because, for example, we are not actually we're not defining in here what happens if I press A for 2 seconds in the alarm setting state. What happens when I press it longer here? I don't know, right? My usual assumption would be nothing happens because it's not specified, but is that a good design, or should it maybe directly go back to the main display without taking me through the time setting as well, right? That could be something I could do. And if I hold down A here in the time display, should it first go to the stopwatch because I pressed time, and that's what this says here, and then after 2 seconds, I should go to alarm setting, or should I wait until the user releases and only then decide whether that was a short press, so I go to the stopwatch, or it was a long press, so I go to the alarm setting? The first solution is kind of confusing. If I do a long press, it takes me through the stopwatch display to the time setting, which is kind of weird. But the second solution kind of is bad because it means that every time I want to just toggle the display, it will take a little longer because I need to press and let go. So this could be a little delay that I don't appreciate, doesn't feel right. Who knows? So this is something, that shows even such a simple device, is super complex. So we need to make that clearer. We would actually have to explain what exactly happens when I depress and release the button, right? Just to make sure that I actually have a proper explanation of this, right? So I would have to say, this is about pressing it and then releasing it again, and that's when I need to go there. So a proper display could look like this. I could decide to say, well, the moment I press A down, I want to immediately go to the time, to the stopwatch. And if I let go immediately, then I want to stay in stopwatch. This was a short press, right? But if I press and I stay for 2 seconds, then a timeout kicks in and takes me to the alarm setting. So we're going for, design option A in our case. Similarly, I could say, if I am in a stopwatch and I press and I release again, then I stay in timer display. But if I press, I get immediately to the time display. If I then have 2 seconds expire, I also end up at alarm setting. That's kind of obvious, right? And here, from alarm setting, the moment I press A, I want to immediately end up in time setting. I don't want to wait for the depress. But if I release A, and no matter how long I take to do that, I want to stay in time setting mode. That's another design decision encoded and made explicit here, right? And then only if I depress A from here, so I press it again, then I end up in the time display. So this is better
than the original version because it makes certain design choices that we have made more explicit. But that's just talking about one button on a simple digital watch. So you can see this is a tricky beast, right? Now, just to go back, to go full circle, originally, first slide, we said, hey, why don't we just write down our user interface in code? And I hope that by now it's clear why you don't want to do this. But I just wanted to reiterate, here's a simple event loop for a word processor. And what it captures, if you look at it a little, then you will notice that this is code for highlighting a selection in text, right? So if I find a button down event on the mouse, I move to the selecting mode and I mark the selection start at the current position. If the button is then, if the mouse moves, I extend my selection to the current position. And if the mouse button goes up, I stop selecting and end it. But this only happens if the mode was selecting, right? So you can see the dialog is in there. The state transition network is in there, but it's very distributed and it's a lot of code and a lot of text to write for a very simple logical explanation. This is why raw code is not the best way to express dialogue logic, right? It merges the dialogue into the business logic of your application, and it is not the best language to express yourself in, and makes it hard to discuss these things with your design team, with users, with clients, and even with your development team. Now, if you want to learn more about these topics in general, I would recommend Dix's chapter 16 and Ben Schneiderman's chapter 5, because he was talking about these various user languages that were extensions of grammars. All right, that kind of wraps it up, really. We have gone in DIS1. I've tried to give you a full tour of 3 things. I wanted you to understand a couple basics of human psychology, because I think these are super important to know about, and they will not become irrelevant in 5 years. Unlike, your current set of Python libraries, these numbers will still be true a couple of years from now. So hold on to these. You'll be able to use them for a long time. Secondly, we then learned about, through case studies, we looked at how HCI has gotten to where it is and how technology tends to evolve from early prototypes to sweet spot devices into often, unfortunately, Baroque devices that overload the functionality due to market pressure. And thirdly, after we've seen how humans tick and what kind of technology we have available in HCI on a very fundamental level, we've gone through the development process. We've shown you how you can use your understanding of human psychology and the availabilities of technology to build appropriate user interfaces by going through an iterative cycle, observing people, developing ideas, prototyping them in paper, in storyboards, in software prototypes, in screenshot prototypes, etc. Make user studies, talk to users, show them your prototype, evaluate with them, maybe also evaluate without them by using tools like GOMS and the KLM model, for example. And finally, if you have arrived at a good interaction design, how to write it down so that it doesn't get mangled in the implementation process that follows. What's next for you? If you found this interesting and I've been able to create sort of a curiosity about how interactive systems actually are being built, then I recommend you check out DIS2. It's a 6-credit class in summer, and this will be much more in the realms of knowledge that you are familiar with as a computer scientist. So it will be a more comfortable class, I would say, because it will talk more about the technicalities about how to implement user interfaces. We are computer scientists and related disciplines after all, so we need to get back to the tech, but we really needed this discourse of DIS1 to get a human-centered view on the problems we're trying to solve. So this will be about all the technical concepts, paradigms, and technologies behind HCI and user interface development. There's a short intro video, I think, that you can watch on the class that should actually be on the DIS2 page. And you can also see the topics there from last year.
and we'll update that in the weeks to come with the topics for next year. But the fundamental structure of the class will remain the same. This class, the second one, I recommend for anybody who's interested in building interfaces or also building systems that will be able to run interactions. So not just apps, but also if you're building the next Windows system for the next class of embedded AI and infused systems, you want to know the stuff that we teach in DIS2. And current topics in HCI is a research class. Yeah, both are master classes. Thank you for pointing out, Ollie. Current topics is a research class in which we teach you how to do research in HCI, and by extension, how to do empirical research in any discipline, really. This is something that you don't learn a lot about in computer science. Our curriculum is largely engineering focused, and you mostly create artifacts. And we want to show you how you can do research and how most of scientific research actually in academia works by running experiments and evaluating results and running studies. And so this is one of the things you can learn from there. It will also give you a nice tour of all the latest and greatest topics that I would say, more technically minded HCI researchers in the world are currently having heated debates about. So we're looking at HCI from our point of view. But we will talk about latest results from the latest conferences and journals in this. So it's a chance to really get up to speed on what's happening in HCI. And here's another hidden secret bonus feature of DIS, of current topics, sorry. In current topics, we will have our PhD students present certain topics that they find of interest in breadth. So if for example, Ollie let's assume Ollie was interested in augmented reality, then he would give an overview of augmented reality research currently, but not just from our lab, but in general, like what's the world doing in HCI research in this. And so it's a great way to meet our PhD students and see if there's somebody that you like, whose topic you find interesting, that you think you want to work with as a master's student, for example. So it's a great way to find out about what our lab is currently up to as well, and find out whether you are a good fit for us as a master's student, for example. So having said that, I want to just say what's next. Well, for now, what's next is your presentations next week. Remember, they are very short, 2-minute video, 4-minute Q&A. We need to see the entire group there. If you do not appear during the final presentations, we're assuming that you are not part of the team and you don't want to be considered as having worked on that final project, right? I need to be this clear, because this is not one person strolls into the Zoom meeting and represents the entire group. This is not how this works. Our questions will be directed to everyone in the team. If we get the feeling that somebody may not know what they're talking about because they've been riding along, we will make sure to ask them questions in particular. And we have to start on time, so you got to be early. So there's a question if we can start these at 10:30. I don't think so, because we were already super for time. And if we move later, Anna, sorry, then we will put other people under pressure who need to be at follow-up appointments after the class. So you may be able to write to Ollie, see if you can arrange for a particular meeting slot in our thing, but otherwise we need to start on time. So be ready, be connected, make sure you test your system ahead of time, that you can present your slides and all that kind of stuff, so that we don't run into any technical difficulties. All right, with that said, if you're interested in a thesis with us, bachelor's or master's thesis, certainly, or a HEVI job, certainly check out this page, hci.rwh.de/jobs. That's where we explain how to best apply for any of those kinds of things with us, so that we can give you good feedback on this. The interface surfaces class, I think what you're referring to may be the seminar, right? Yeah, that's a seminar. So seminars were already announced for the summer, and I think the selection process already wrapped up. Yeah, that's all done. So seminars for next semester are already distributed.
Well,
I hope you. Go ahead, Ollie.
the selection process happens at the moment. So if you are selected at the moment, this is totally fine. This will happen in the upcoming days.
Yeah. Okay. With that, I'd like to thank you guys all for being there. Thanks for playing along and participating where possible. I know working from home is kind of sucks, and we hope to be able to do DIS2 in presence. There was a question about remote attendance. If the class moves to a present format, you'll definitely have to be in the class to take part, because there's assignments you need to do and group work you need to do. And so you'll have to be studying in Aachen to take the class. But that's true for the entire computer science program. Our program is a presence program normally, if we're not riddled by Corona. So expect to be back in Aachen and taking our classes. All right. Okay, yeah, we'll prepare the videos and play them. Thank you, Oli, for clarifying that, so people don't need to play the videos. I don't want to scare anybody. All right, good luck with your final preparations for your presentation next week. I really look forward to seeing your projects. And good luck with the final. And hope to see many of you, not just in the presentations, but also next semester. Thank you.
This content was provided by RWTH Aachen University.